Hello students, my name is Sumit Sagar Hota. I am a PMR PG student IIT Palakkad. Today we will discuss lecture 31 to lecture 35 by Professor Ashok Desai, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion by NPTEL. This is the week 7 of the live discussion section. In these sections we will cover some of the theoretical MCQ questions and one long problem, and which consists of some of the short questions, okay, which will be helpful in your numerical point of view. Okay, so let's start the section. So the first question is, in a turboprop engine, the expansion of gas takes place partly in dash and partly in dash. Okay. Okay. So the answer to this question is, in a turboprop engine, as the name suggests, turbo means there is a turbine is there, so some part is there in turbine, okay, some expansion down in turbine, okay, and next propeller is there, but with turbine one more thing is connected, which is a nozzle, okay, before exhaust nozzle is also connected, so that in that nozzle some of the expansions are also taking place. So in a turboprop engine, the expansion of gas takes place in turbine and nozzle. Okay. Okay. Okay, so now we know in the turbine and in nozzle this expansion is taking place. So how much expansion taking place in turbine and how much expansion taking place in nozzle? Okay, so most of that expansion actually taking place in turbine, and whatever the left, that is taking place in the nozzle. Okay, in a turboprop engine, more particularly if the number we have to tell, okay, it's 80% in the turbine and 20% in the nozzle. Okay. Okay, the next question is, the turboprop engine can operate economically over a wide range of speeds. Okay. Okay. So is it a true or false? Okay. So the condition is it it can operate in wide range of speed. Okay, so most of the turbo J, turbo A, they can operate over wide range of speed, but the real question is it really operate economically? This is important. Okay, is it really operate economically or not? Okay, so that's the real question. So for the turboprop engine, it can operate actually in a economically under wide range of speed, and those what is the range we'll see in the later questions. Okay. Okay, so next question, the frontal area in a turboprop engine is more than in propeller engine, so the drag is reduced. Okay, that means it's a comparison based question. Here it's compared between the turboprop and the propeller engine. Okay, so obviously the turboprop engine is actually advanced version of the propeller engine. Okay, so the drawback of propeller engine is it's having very high frontal area, and due to which there is a enough amount of drag is produced while there is a while the flight is there in the okay in the sky. Okay, so yeah, so to reduce that, the design of turboprop engine introduced. Okay, so in the case of turboprop engine, the frontal area is less as compared to the what propeller engine. Okay, so this statement is false. Okay, frontal area means the area which just contact with the flow direction. Okay, or more specifically perpendicular to the force flow direction. Okay, if there is a cylinder is there and the flow is along the length of the cylinder, then the frontal area is the cross section of the cylinder. Okay, so it's just an example. Okay, similar way you can relate with the this propeller and turboprop engines. Okay. in a turboprop engine at high speeds, the propeller efficiency is what? Okay. This is a kind of most of the engines, this is the problem will be there. Okay, so that's the reason why we are actually redesigning these engines, okay, to increase this propeller efficiencies. Okay, so yeah, the disadvantage of this turboprop engine is at high speed, the whatever the propeller efficiency is there, it is going to decrease. Why? Because there will be enough drag which will actually which will what you called which will alter the propeller efficiency. Okay, so yeah, so for high speeds it's not going to be a suitable engine to operate with. Okay, so the reduction gear exists in a turboprop engine, is it true or false? It's actually a true statement that there exists a reduction gear in the turboprop engine. Okay, what does this reduction gears do? This gear mechanism either will increase the speed or decrease the speed, okay, of the propeller. Okay, so obviously here we don't want to decrease the speed, obviously here we want to increase the speed of the engine. So for that, reduction gears are there, means 5:1, 1:5. Okay, one bigger size gear and one smaller size gear. Okay, if the motion will transfer from a bigger size gear to a smaller size gear, then the speed will what going to increase. Okay, so those things are there in the our how do you call turboprop engine. That's so in that way, to from higher teeth, we can tell higher teeth gears to the lower teeth gear or the higher size gear. Both things actually matters. Okay, what is the number of teeth, what is the size of the teeth, and what is the diameter of the gear, everything matters. Okay, and and then what is the rpm in which these gears will rotate. Okay, so those things by reduction in all these things from higher rpm to the to the higher size gear to the lower size gear, we can actually increase the what rpm of the or the revolution of the what gear. So in that way we can actually go to a very high speed operation of the turboprop engine. Okay, so that's the reason why in the turboprop engines, especially when there is a propeller operated, fan operated, all these kinds of mechanisms, turbofan, turboprop, all these engines, there exists a fan or there is a propeller is there, and the increment in velocity is required for these kinds of engines, and in those engines there is a reduction gear mechanisms are always exists. Okay. Okay, what is the then next question? The reduction gears in a turboprop engine dash the cost and consumes certain energy. Okay, obviously if there is a gear mechanisms are there, reduction mechanism, that means more number of gears are used, and gears are not a very cheap product. Okay, so manufacturing of gears with a particular number of teeth, all these things is actually a costly operation. Okay, so because of that extra part we have actually okay, so there is extra part, so the cost will be obviously high. Okay, and obviously so there is actually a reduction in gear gear mechanism, due to which some power wastage will be there. Okay, from the turbine shaft, some of the power wastage will be there because of this reduction mechanism, because they are not 100% what you call efficient. Okay, so that's the reason why it consumes both. It's having some cost as well as it is actually consumes some energy of the whole system, but the outcome of this thing is very high. So that's the reason we are actually using, because it's actually going to increase the speed very high, maybe 5 times or 10 times. Okay, so that's the reason why we are actually using this reduction gear in turbo prop engine with all these disadvantages. Okay. Okay. So next question, the turboprop engines are widely used in where? Okay, so the turboprops are actually, if you really see in the what you called cargo aircrafts, okay, in the military department, there you can see for taking higher loads we are actually using this turboprop engines. And also if you can see our commercial, okay, it's more specifically, if you see the commercial, there is no turboprop systems are there. Rather, if you see the small flights, because in commercial mostly turbojets there are used, okay, nowadays. But if you see the kind of some private pilot means private jets, they are actually this turboprops are actually used, especially the people of high rank peoples, those peoples actually having their personal aircrafts, those peoples actually using. But with also specifically business class peoples, all these peoples are actually using this commercial what do you call means this turboprops they are using. So but initial stage so but for the initial times, there in the commercial aircrafts, these turboprops engines are actually used. That's the reason why this question are actually set. Okay, so now also it's using in the commercial purposes. Okay, and the commercial here does not mean the for only for the peoples. Commercial also means that it's for the cargos. what type of aircrafts are used. So in military as well as in commercial purposes, we are actually using the turboprop engines. Okay. So the next question, the turboprop engine is very flexible and having a good fuel economy. This is actually a true statement. So it's actually a comparative statement. It's a good fuel economy as compared to the propeller engine, and it's more flexible as compared to the propeller engines. You can like this is actually the full question, but yeah, it's actually question. In this kind of question you have to actually relate what is the previous engines before the turboprop engine, and accordingly you have to answer the questions. Okay. Okay. Okay, so I already told wide range of speed it can operate. So now this is the answer of that. What is the wide range of speed it can operate? The turboprop engine, it's actually 400 to 600 kilometer per hour. This is a wide range of speed it can operate. Okay. And if it is going above 600, then the efficiency of the propeller efficiency will going to decrease for the turboprop engine. Okay. Okay, the Rolls-Royce developed a E2100 based on the T56, but with a free power turbine with an output of dash kilowatt, and this was used in C-130J and C-27 military transport. Okay, it should be noted that Rolls-Royce is not only producing the commercial cars, so rather it's actually producing the gas turbine engines. Okay, and so that's the key factor of what a Rolls-Royce company. She initially produced, now also they are producing. Okay, and So yeah, so if you really going to see it, this is actually a, what you call, if you know this exactly, the engine AE2100, it's because this is the most famous engine by Rolls Royce actually. That's the reason why, and it's actually going to very good output it's actually going to give. That's the reason why this question I just set, because this kinds of question can be actually asked. Okay, because this is the engine also used in military purposes. Okay, especially for the cargo aircrafts. Okay, so yeah, so that's the reason this question is very much important. Okay, and if you know else, actually if you don't know any of these things, if you only know how much power required for a cargo military transport aircraft, okay, you can actually see in this more or less similar range. If you know that value, no need to actually remember whatever this AE2100, nothing to actually remember. Okay, if you know actually how much power it can generate for a military transport aircraft for a very good economy, so yeah, that's the idea. It's actually more or less in the range of 4500 kilowatt. Okay, so that's the idea. Okay, so the turbo shaft engine in which the output power drives a dash rotor. Okay, first of all, what is the example of a turbo shaft engine? The best example will be what? A helicopter. Okay, helicopter is the best example of a turbo shaft. Turbine is there, and one, because of in that one shaft we are just providing the blade, okay, fan blade, and which actually creates a downward thrust, and the back tail fan actually helps in balancing that thrust, because if there is no tail fan, the instead of only, it's what you call, instead of only going up or directly go up, it will actually rotate, the whole helicopter will rotate. So to balance the helicopter, the backside fan is there for a helicopter, and the upside fan is only for to give the thrust. Okay, and so that's the idea for your what helicopter or a turbo shaft engine. Okay, so now the question is the turbo shaft engine in which the output power drives a rotor. Okay, so example is, you can write it directly, write down the name of the okay, here actually they asked the name of the turbo shaft engine. You can directly write down helicopter. Okay, helicopter is the answer. Okay, okay, so also there is a speed limitation for a helicopter. Okay, so it cannot go very high speed, because you see I already told, because of the first there is a weight limitation. Okay, because already there is too much weight in the helicopter and that much thrust it cannot generate, then it cannot go that much high speed, as well as this instability instability is a big problem, because if you actually really going to see some of the helicopters having one thrust, one what do you call thrust capacity, one thruster or one fan. But if you see military aircrafts, military helicopters, some helicopters are being actually two fans, okay, to carry more amount of soldiers to the, okay, and to move in a very high velocity, okay, as compared to a one single fan. So yes, so the new design is always a for the progressive approach, and new designs are performed. This 160 knots is the, so here the answer will be 160 knots. This actually we talks about the helicopter with only one single fan, so the speed limitation is 160. But if we go for double fan based helicopters, it can be beyond 200 knots we can actually achieve. That's actually nowadays used in the military purposes, okay. So yeah, so every design having its disadvantage and advantages, but in single blade is actually lightweight helicopter. Because of its lightweight, it can actually if you reduce the weight, and so in that way we can actually go very high velocity. So that's also one advantageous in this case, okay. And smaller size helicopter very difficult to track by the enemies. So yeah, that's also one more advantage, okay. And and one more thing is that we can actually rotation of the helicopter, we can rotate, and we can have puts lots of guns, all these things. So these are all some of the way of thinking. So why the speed is limited to in a certain value, okay. So higher velocity is also not a very advantageous thing, lower velocity is also not a very advantageous thing. It should be in a range whatever it's required by the person who are actually using the helicopter, okay. So it's set to a value somewhat 160 knots per a this is the maximum value you can tell, okay. And beyond that it's actually not possible, okay. So yeah, but by changing the design and lightweight, all these things I already told, it can be go beyond 200 also, okay. So okay, so Rolls Royce, okay, there is two kinds of engine actually. It's given Rolls Royce and PWC 200 and two Rolls Royce 250, and it uses a turbo shaft, okay. So if you don't know these Rolls Royce and PWC, all these things, if you know only the what kinds of compressor used by a turbo shafts, okay, you can actually answer the question. If you just see these two names and you don't know two names and you just leave the question, then obviously you lose the marks. But rather if you just think about this whatever the what type of compressor we can use in the turbo shaft engines, then it will be a very good options. And if you know actually Rolls Royce and this just heard about these names where these Rolls Royce engines, all these engines are actually used, then you can very easily answer this question. Most of the cases Rolls Royce used in the military purposes. So and in those cases, and PWC both in commercial as well as military purposes they are used, and for that you need a very what you call very powerful compressor, which is a centrifugal compressor actually you actually need, because there are space limitations, all things are there. That's why general axial and reciprocating compressors cannot be used as compared to a centrifugal compressor, okay. So yeah, so and in old times centrifugal compressor actually very well used, okay, in these kinds of engines, okay. So yes, the answer is a centrifugal compressor. Okay, the Rolls-Royce 250 and PwC 200 turbos are limiting the cycle pressure ratio up to about dash. Okay, so limiting means what is the maximum pressure ratio, cycle pressure ratio. Cycle means whatever the cycle it is. A turbine engine operated on which cycle? Obviously it's a Brayton cycle. Okay, so in that Brayton cycle, what is the pressure ratio you want? Okay, so any kind of turbine engines mostly just operate up to a value of nearly 10. Okay, it cannot be more than 10. Okay, so and they asked limiting means they want the maximum value. Okay, so 5 cannot be the case, 15 and 19 it cannot go. Okay, so the option A will be the correct answer. Okay, so 9 and 10 it can actually go. Okay, T800 jointly developed by Rolls-Royce and Honeywell turboshaft uses dash. Okay, I already down told Rolls-Royce always uses what? Centrifugal compressor. Whatever just combined with them, they have to use the what do you call centrifugal compressor. Okay, so if you see in the three options, the centrifugal compressor is common. Okay, especially for a turboshaft engine, the centrifugal compressor is very commonly used compressor. Okay, now let's talk about the what? Staging. How much staging they will actually used. Okay, so staging actually enhances the mixing. Okay, and so that's the reason more energy we can actually energy cascading will be there, and we can handle more higher amount of energy or higher amount of heat more precisely, if I can tell. So that's the reason of staging in a centrifugal compressor. So yes, so same thing also done in the turbines also. So yeah, so staging always helps the mixing. So single stage obviously cannot be the case. Then why this question is asked? If the share is single stage, okay, so there will be multiple staging. Yeah, now means this T800 is actually a little old engine, so that's the reason two staging is there, but now actually 3 and even more 4 or like that nowadays actually it's used. Okay, so in T800 is actually first time they actually used the multiple staging in the centrifugal compressor. So yes, so that's the idea. So A is the correct answer. Okay, most of the people are actually going to choose A and C, which is a wrong option, because if they don't know about T800, they will directly choose multi-staging, which is a 2 and 3, and this will be a wrong option. Okay, so you should know actually when this T800, Honeywell, all these things are introduced. Okay. Okay. So let's start the problem. This is a lengthy problem, but this is actually very much helpful. These 5 kinds of questions you can be asked in your exam, or the single question. Okay, start the question. A jet propelled plane consuming air at a rate of 18.2 kg per second is to fly at a Mach number of 6 at an altitude of Mach number of 0.6 at an altitude of 4500 meter, and the pressure at the ambient cases are 0.55 bar and 255 Kelvin. The diffuser, which has a pressure coefficient of 0.9, decreases the flow to a negligible velocity. The compressor pressure ratio is 5 and the maximum temperature in the combustion chamber is 1273 Kelvin. After expanding in the turbine, the gases continue to expand in the nozzle to a pressure of 0.69 bar. The isentropic efficiency of the compressor is 0.81 and a turbine of 0.85 and of a nozzle of 0.915. The heating value of the fuel is 45,870 kilojoule per kg, assuming Cp as 1.005 kilojoule per kg Kelvin, that is a Cp of air, and Cp of the gas 1.147 kilojoule per kg Kelvin, gamma of air 1.4, gamma of gas 1.33. So we have to calculate the power output of power input to the compressor, power output to the of the turbine, fuel air ratio, thrust provided by the engine, and the thrust power developed. Okay, this is the question. It's actually a very good example of jet propelled or turboprop engine. Okay, Okay, so for solving this question, first of all you have to draw the cycle. Okay, there is a TH diagram. Okay, Okay. Okay, so let's draw the cycle. Just now start the what jet propelled plane. Okay, jet propelling engine. Okay, so just going to so let's start the solution. Okay, so what are the things given? We just write down. Okay, so what is the isentropic efficiency of the compressor? 0.81. It's actually not required to write down everything whatever given, because we directly use it. Okay, not required, directly we can use it, because if we write down it will be very time taking. So what I will do, directly write down what is the T1 dash. Okay, so T1 dash. Okay, so A2, how to find out T1 dash? We can if you see in TA, if we add the whatever the velocity head, then we can actually get what our T1 dash. Okay, so this is a formula for T1 dash is, for the isentropic whatever the process, we are assuming bi square by 2cp. Okay, we know what is the Mach number, 0.6, which is equal to vi by square root of gamma r into T ambient. Okay, from here we can calculate actually vi, because all the other things are actually given. Okay, (1.4) 287, TA given 255 Kelvin. So if you solve it, you will get vi as 192.06 meter per second. Okay, so next, just substitute in the formula of T1 dash and find out the T1 dash. TA plus bi square 192.06 2 into Cp. Okay, so 1.005 into 10 to the power 3. You solve it, you will get T1 dash as 273.35 Kelvin. So now I need to know what is the ramming efficiency already given. So what is the use of that ramming efficiency, now we'll get to know. Okay, ramming efficiency 0.9 given, which relates the P1 and P ambient pressures. Okay, the ratio of difference of P1 and P ambient. Okay, now we actually have to use the isentropic relation between the point 1 and A, right? Because anyway T1 and T1 dash is actually same, so PA is your 0.55, T1 is your 273.35, TA is your 255. Okay, and gamma is your 1.4. Okay, so if you solve it, P1 dash is equal to 0.55. We write down next page. So P1 dash is equal to 0.55, 273.55 divided by 255 into to the power 3.5. So what is P1 dash? 0.70144 bar. Okay. So next you substitute in that ramming efficiency formula. Okay, because we have all the things given. Okay, we have to find out now P1. V1 minus PA 0.55, P1 dash minus PA. If you calculate, you will get P1 as 0.6863 bar. Okay, now next process will be the, now ramming is over, next come to the compressor, okay, which is a process 1 to 2 or 2 dash. Okay, so now in compressor, the isentropic efficiency of the compressor 0.81. So let's apply the isentropic relation for the 1 to 2 process. We know P2 by P1 is 5, it's given in the question. Okay, so what will be the T2 dash? Whatever this ratio is, if you just solve it, it will comes out to be 2 by 7, okay, of the gamma. Okay, so now just solve it, it will gives you the value of T2 dash, which is 432.94 Kelvin. Okay, so now substitute in the isentropic efficiency formula and find out the value of what? T2. Okay, okay, so next we can directly, we have everything to get the value of the compressor work. So just let's find out. Okay, similar way we can also calculate the fuel to air ratio. Okay, so how you can calculate? You can calculate it from the formula of heat addition. Okay, but assuming combustion efficiency as 1. Okay, which is a theoretical assumption. Practically it's not possible. So if you solve it, you will get small f value as this. And what is this small f? The small f is your fuel to air ratio. This is the third bit answer. Okay, now the next target will be to find out the turbine work. Okay, and to okay, so in the question one more thing should be given, which is your T4, which is your turbine exit temperature. Okay, so this T4 value will be 1104.125 Kelvin. This should be given, otherwise you cannot solve this question. Okay, so let's find out the m dot f. Okay, so we know f is equal to m dot f by m dot a. Okay, so we need m dot f is equal to f into m dot a. What is f? 18.2 into, sorry, what is m dot a? So the f will be 0.02223 into m dot a is 18.2. So take small f. So m dot f will be 0.405 kg per second. If you see m dot a, we already find out. Okay, this is your m dot a. Okay, this is actually I think given in the question. Yes, 18.2 kg per second. Okay, is in the question given. Okay, how much, what is the air flow rate? Okay. So exactly, so this is your m dot f. Okay, okay, so what is the formula for turbine work? M dot A plus M dot F into Cp of gas into T3 minus T4, M dot A into 1 plus F into T3 minus T4. Okay, what is M dot A then? Substitute all the values and get the answer of turbine work. The turbine work is 3603.713 kilowatt. Okay, with the second bit of the answer, let's find out the isentropic efficiency of the turbine. From there we can calculate T4 dash. Okay, okay, so now let's apply the isentropic relation between T3 in the 3 and 4 for dash position, or 3 and 4 position, whatever. Okay, so your T3 is 1273 Kelvin and T4 dash is 1074.32 Kelvin. Okay, so and you know very well P3 by P4 is equal to what? RT is equal to 1.98. Okay. Okay, so and P4 is equal to P4 dash. Okay, so that means we can actually get your P4 dash as P3 by RT. Okay, so P3 means your okay, because you know very well your okay, we know P2 by P1 equal to 5. Okay, and what is your P3? P3 is equal to what? P2. We know also what? P3 is equal to P2. Okay, and P2 by so you also know P2 by P1 is equal to what? 5, and P1 is your 0.6863 bar. Okay, so what is P3? P3 is equal to now P2 into, okay, so 5 into 0.6863 divided by RT, which is your 1.98. Okay, so you'll get a P4 dash as equal to P4 is equal to 1.732 bar. 1.732 bar. Okay. Okay. Okay, so now what I'll do, okay, so here's how you get RT, right? You'll get from this formula. Okay, okay, so next we need to find out the pressure ratio in the nozzle, P4 dash by PA, which is 1.732 divided by PA will be your 0.55, 3.1486. Okay, so what is the critical pressure ratio? P4 by PC, one divided by 1 minus gamma minus 1 divided by gamma plus 1 eta of n. Okay, to the power gamma by gamma minus 1, and what is the gamma? 1.33, and eta of n given in the question 0.915. Okay, so now if you actually put it all these values, your PC is equal to P4 by 1.97. what is the P4? 1.732. we'll find out. Okay, 1.97 from this formula, and your okay, P4 value is already given. Okay, and so obviously we already find out. Okay, so from there we can find out critical pressure as 0.8794 bar. Okay, this is very important pressure. This kind of question can be asked. Okay, so what is the critical temperature? 2 by gamma plus 1 into what? T4, 2 by 2.33 1104.125. okay, so now if you solve it, that critical temperature 947.75 Kelvin. This is your critical temperature. Okay, so what is the jet velocity? V jet is equal to square root of gamma r into critical temperature. This is the reason why we need the critical temperature for the exhaust. What is the critical velocity? All this thing. Okay, temperature, sorry, the r value at the exhaust already we have to find out. Okay, or already if it is given, it's good, otherwise you have to find out. Okay, yeah, means it should be actually given in the question. What is the r value at the exit or at the critical conditions? Okay, so the value comes up to be 284.6. okay, now you just solve it and find out the jet velocity. 598.95 meter per second. Okay, next we will find out the critical density. Okay, apply the ideal gas equation. We are assuming it as ideal gas at the exhaust. So now we just find out the total mass flow. Okay, m dot a plus m dot f rho c into an into bj. An is equal to so an is the area of flow. Thrust provided by the engine. Okay, so now we just find out the what thrust and the thrust power. These two things, it will take max 5 minutes. Okay, thrust provided by the engine, F is equal to ma into 1 plus f. This is the formula. Okay, bj minus bi plus an into pc minus pa. Okay, all these values already I just find out. Okay, and all things are given. Okay, just substitute and get the answer. One 10708.78 Newton. This is your answer. Okay, next is the thrust power. P is equal to F into Vi. Many people do the mistake, they will multiply with the jet velocity. Okay, don't multiply jet, always multiply with Vi. Okay, inlet velocity. Okay, don't multiply with jet. Okay, okay, okay. Okay, with this we end the section. Thank you very much for attending the section. If you are attending the recorded one, also thank you very much. In this section we will cover some of the MCQ and some of the problems, and okay, so we will meet in the next week 6 to 8. in the week 8 of the live discussion section. Thank you very much, and good night, and have a nice day.